We have our new function, the inverse trig function. But so we can make use of it, obviously we need to know how to do calculus with it. So differentiating the inverse trig, let's start with inverse sine. But fortunately, we do know how to differentiate regular sine. So if I make x the subject here, so I'll rewrite it, make x equals sine y. That I can differentiate. But it'll be dx to y instead of dy dx. So if I turn it upside down, I've got my derivative. It's just in terms of y rather than in terms of x. Now, we tend to like it in terms of x, so let's rearrange this. All I know is x equals sine y. How can I rewrite cos y in terms of sine y? Well, we've got a trig identity, but it doesn't relate sine and cos. It actually plays with sine squared and cos squared. So what I do is I make the cos y the square root of cos squared, and then the cos squared I can change to 1 minus sine squared, and then the sine squared is x squared. And so there's my derivative for inverse sine, 1 over the square root of 1 minus x squared. All right, let's try cos. So we'll make it cos. Differentiate cos, we get minus sine. Turn it upside down, and we'll do a similar thing. We'll turn the sine y into the square root of sine squared. Sine squared is 1 minus cos squared, and we get a very similar expression, the only difference being the negative, of course. So inverse cos, we get negative 1 on the square root of 1 minus x squared. How about tan? Well, tan y, differentiate tan, we get sec squared. Turn it upside down. Well, I don't need to do the square root of the square. It's already squared. Sec squared is the same as 1 plus tan squared. And so we get 1 on 1 plus x squared. So they're the three basic ones. But to make it more useful, let's generalize them. If it's just a linear function, so if it's just x on a as a linear function, then it's 1 over the square root of a squared minus x squared. Inverse cos becomes minus 1 over the square root of a squared minus x squared. And inverse tan a over a squared plus x squared. So the thing we have to be careful with there is inverse tan has a on top. That's a very common mistake to leave 1 on the top because, of course, the others have 1 as well. But I personally prefer this one because then it's consistent. Inverse sine, derivative over the square root of 1 minus the function squared. Inverse cos, minus the derivative over the square root of 1 minus the function squared. And inverse tan, the derivative over 1 plus function x squared. So each one of those does have the derivative on top. Let's look at an example. Y equals the inverse sine of 5x. 5x is a linear function. So I could use the first one. But it's quicker to use this because I can do it all in one hit. All I've got to do is say the derivative of 5x is 5. It goes on top, over the square root of 1 minus the function squared. Square 5x, you get 25x squared. So, hey, you got the answer all in one go. Oh, the inverse swimming question. Inverse cos x. Minus the derivative of e to the x is, of course, e to the x, over the square root of 1 minus the function squared, so 1 minus e to the 2x. X on 3. Again, linear function. But this time, because the number's in the bottom, it's actually quicker to use the other one, because then I can just go, oh, it's 1 minus the square root of a squared minus x squared. If I did do it the other way, so if you just want for consistency, just to remember one way of doing it, that being derivative on, it still works, because this is what happens. We go derivative, well, the derivative of x on 3 is a third, on the square root of 1 minus the function squared. So 1 minus x squared on 9. Fractions on fractions. So to get rid of the fractions on fractions, we multiply. They actually do have the same denominator, even though they look different, because of course the 9 is under the square root sign. So we're multiplying top and bottom by 3. Just to highlight that, I've factorized out the third in case you didn't believe me, that on the 9 is actually over 3. And we're left with the square root of 9 minus x squared on the bottom there. E to the inverse cos x. So instead of inverse cos of e to the x, it's e to the inverse cos of x. So this time it's an exponential that I'm differentiating. Differentiate an exponential, you differentiate the power. Or what's that? Power. Okay. Differentiate the power, inverse cos x, we get minus 1 on the square root of 1 minus x squared times e, and the power doesn't change. Some people like to write that all as one fraction, like me. I'm one of those people. Minus e to the inverse cos of x over the square root of 1 minus x squared. Ooh, anarchy. Bring down the power. Okay, so bring down the power. 3, lower the power. 2. Diff the inside. Well, the inside is inverse tan of x. Differentiate inverse tan of x, we get 1 on 1 plus x squared. So let's just tidy that up a little bit. There we go. 3 times inverse tan of x squared over 1 plus x squared. Ooh, product rule. Write down the first, x squared. Diff the second. So the second is inverse tan of x cubed. Differentiate x inverse tan of x cubed. The derivative, 3x squared, over 1 plus the function squared. So x to the 6 there. Plus, write down the second, inverse tan of x cubed. Diff the first, 2x. Tidying that up, I didn't bother putting it all as one fraction. 3x to the 4 and 1 plus x to the 6 plus 2x inverse tan of x cubed. Are we getting some really good derivatives now, or what? Good. No one said what, therefore we are getting good derivatives. Exercise 1D.